Welcome to chemistry classes. In this video we are going to discuss about states of matter part 3. Okay, previous video we discussed gas laws, Charles law and Boyle's law. We discussed Boyle's law and Charles law. Next one we have to discuss here Gerusack law. Okay, Gerusack law means it is pressure temperature relation. According to Gerusack law, pressure of a given mass of gas, or you can say pressure of a fixed amount of gas directly proportional to temperature at constant volume. Okay, pressure of a given mass of gas directly proportional to temperature at constant volume. Isochord. We will say isochord. Okay, we already discussed isotherm. Okay, isotherm, Boyle's law. Isochord, Charles law. Isochord, Gerusack law. Gerusack law. Okay. So here pressure directly proportional to temperature, so we can change directly proportional to equal to, so we can do P equal to K3 times T. P equal to K3 times T. Okay, so here you can rearrange the equation, bring T over here, so P by T equal to K3, P by T equal to K3. Already we did K1 and K2, that's why we used a different proportionality constant K3. Okay, so here graphical representation, pressure against temperature, this is isochord. Here we have different lines at a different volume. We know at a higher pressure, this is higher pressure. At a higher pressure, volume will be less because pressure and volume inversely proportional. So here V1 will be less than V2, V2 will be less than V3. Okay, so here P against temperature, they are directly proportional. So we will get a straight line. Okay, and here when you decrease volume, the graph will shift upward, or you can remember like this: at a higher this region, high pressure means less volume, so V1 will be less than V1 less than V2 less than V3. Clear? So these are the things you have to understand in Gerusack law. Next one we have to discuss here the last gas law. We have to understand here Avogadro law. Avogadro's law mean here this is volume and number of moles. Okay, so here pressure, temperature, volume constant. Here Avogadro law mean volume number of moles relation, Vn relation. Volume number of moles relation, and here temperature and pressure will be constant, two variable constant, temperature and pressure constant, volume of a given mass of gas directly proportional to number of moles of gas. Okay, volume of a fixed amount of gas directly proportional to N mean number of moles at constant pressure and temperature. V directly proportional to N, so proportionality change to equal to, so V equal to K4 times N. Already we use K1, K2, K3, that's why we use a different proportionality constant, V equal to K4 times N. Okay. Also you remember two more point. 1 mole of any gas, it contains 6.022 into 10 power 23 particle. This number is called Avogadro constant. You learned this previous chapter. Okay, so 1 mole of any gas consists of 6.022 into 10 power 23 particle. This number is called Avogadro constant. Also you remember 1 mole of any gas at STP, at standard temperature and pressure, 1 atmospheric pressure 25 degrees Celsius, this is standard temperature and pressure. At standard temperature and pressure, 1 mole of any gas contains 22.71098 liter per mole. Okay, so remember this, at STP 1 mole of any gas 22.71098 liter per mole. Okay. Okay, so here we are talking about Avogadro's law. According to Avogadro's law, volume directly proportional to N, V equal to K4 times N. Okay, according to number of moles, we are talking about number of moles. In previous chapter, you learned number of moles is equal to mass over molar mass. Okay, mass over molar mass. For example, 2 gram oxygen molecule, 2 gram oxygen molecule. So given mass is 2. Mass of oxygen is 2. So small letter m mean given mass, that is 2. And here capital letter M mean it is molecular mass or molar mass. You know oxygen atomic mass 16. 2 oxygen atom here, 2 times 16. So molecular mass of oxygen 32. So this is small letter m, given mass 2 gram. Molecular mass of oxygen 32, that is molar mass. Okay, so here V equal to K4 times N. N mean number of moles, mass over molar mass. Okay, you rearrange the equation. We know the equation V equal to K4 times N. Substitute the value of N over here. So you can write V equal to K4 times K4 into M divided by capital letter M. M by M. Rearrange the equation. So M equal to, okay, bring this M over here and bring V over here. So capital letter M equal to K4 into small letter m divided by V. That is written here. Capital letter M equal to K4 into M by V. M by V, mass per unit volume mean density. Okay, so capital letter M is equal to K4 into D. D mean density. Clear? So using Avogadro's law, we can find molecular mass of a gas. Using Avogadro's law, we can find molecular mass of a given substance. After understanding molecular mass of gas, we can identify the given gas. Okay, so how can you find? What are the information you need to find molecular mass? You need K4, you need proportionality constant, and also you need density of that gas. Okay, also K4, if you have K4, mass and volume also you can find. Mass by volume mean that is density. Okay, so here we learned different law. Boyle's law mean volume pressure relation. Charles' law, volume temperature relation. Avogadro's law, before that Gerusack law, pressure temperature relation. Now Avogadro's law, volume and number of moles relation. Okay. Okay, next one we have to discuss here ideal gas equation. Ideal gas equation. Ideal gas equation means it is combined gas equation. Charles' law, Boyle's law, Avogadro's law. Okay, these three laws combined, we can say ideal gas equation. According to Boyle's law, we know volume is inversely proportional to pressure. Pressure is inversely proportional to volume, or you can say volume is inversely proportional to pressure at constant temperature. Charles' law, volume directly proportional to temperature at constant pressure. Avogadro's law, volume directly proportional to number of moles at constant pressure and temperature. Okay, when you combine this, look here, left hand side all V. So V directly proportional to NT. Okay, here NT divided by P. So these three laws combined, you can say volume directly proportional to NT divided by V. Bring the NT divided by P. Okay, bring P over here. So you can say PV directly proportional to NT. PV directly proportional to NT. You change directly proportional to equal to, so you have to multiply with a constant. This constant is R. We will use a letter, capital letter R to represent constant. This constant called gas constant, universal gas constant. Okay. So you can say here V equal to nRT by P. Bring P over here, PV equal to nRT. This is ideal gas equation. PV equal to nRT. Very important equation in chemistry. PV equal to nRT. PV equal to nRT. So look here, PV equal to nRT. So R is equal to PV by NT. Okay, R equal to PV divided by NT. Okay. Consider 1 mole of gas at 1 bar pressure. Temperature is 273.15. Volume is 22.71 liter per mole, or you can say 22.71 into 10 raised to minus 3, 22.71 into 10 raised to minus 3 m cube. This is the volume. Okay, so the value of R, we can find value of R at this condition. 1 mole gas, temperature is mentioned, volume is mentioned, pressure is 1 bar. 1 bar pressure means it is 10 raised to 5 Pascal. So substitute these values over here. Pressure, volume, number of moles, temperature, all these values substituted over here. 10 raised to 5 Pascal into 22.71 into 10 raised to minus 3 divided by 1 mole into 273.15. So when you solve this, you will get 8.314. 8.314. Look here, 8.314. You have different value for R. If the unit is different, okay, different unit, 8.314. First one, simply you can say 8.314 Pascal m cube per mole per Kelvin. That is first unit of R. Look here, Pascal here, m cube here divided by mole. So it will be per mole per Kelvin. This is 1 unit of R. Okay, 8.314 Pascal m cube per mole per Kelvin. And another one, 8.314 into 10 raised to minus 2 bar liter per mole per Kelvin. Bar liter per mole per Kelvin. Okay, so this is the second unit. Third one, 8.314 joule per Kelvin per mole. 8.314 joule per Kelvin per mole. Okay, so remember 3 different units of R. Okay, first one 8.314 Pascal m cube. Pascal m cube per mole per Kelvin. Second one 8.314 into 10 raised to minus 2 bar liter per mole per Kelvin. Per mole per Kelvin. Third one 8.314. Second one only here 10 raised to minus 2. First and third only 8.314. 8.314 joule per Kelvin per mole. So these are the different values of R. Okay. Okay, so here we discuss ideal gas equation. According to ideal gas equation, PV equal to nRT. PV equal to nRT. Okay. Here consider a fixed amount of gas. Next one we have to discuss here related to ideal gas equation. Consider a fixed amount of gas. Okay, a fixed amount of gas, its initial pressure P1, initial volume V1 and temperature T1. Okay, after certain change, this pressure P1 change to P2, volume change to V2 and temperature change to T2. P1, V1, T1 change to P2, V2 and T2. Okay, so we know according to ideal gas equation PV equal to nRT. Here N and R, it is constant. N mean 1 mole gas, R mean universal gas constant. Both are constant. And others are variables P1, V1, T1. Okay. So here we can write here rearranging this equation PV by T equal to NR. Okay. Rearrange this equation PV by T equal to NR. So see here, this is the initial condition for the gas. So we can say here P1 V1 divided by T1 equal to NR. NR no need to say N1 R1 because NR it is constant. P1 V1 divided by T1 equal to NR. After certain change, this variable changed. So we can say P2 V2 divided by T2 equal to NR. P1 V1 divided by T1 equal to NR. P2 V2 divided by T2 equal to NR. Okay, so here right hand side in both equation, right hand side same. So we can say P1 V1 divided by T1 equal to P2 V2 divided by T2. We can write it like this. Okay, so this is called combined gas equation, and we derived this equation from ideal gas equation. This is combined gas equation. Okay, so we know here next one we are going to talk about ideal gas equation and density. Density, okay, density, relation between density and ideal gas equation. We know ideal gas equation PV equal to nRT. PV equal to nRT. Okay, so after rearranging this equation n by v, okay, bring v over here. So n by v equal to p by RT. Okay, look here, bring v over here. So n by v, it will be n by v. Okay, and RT bring over there. So p by RT, n by v equal to p by RT. Okay, we know n mean number of moles. How to find number of moles? Mass over molar mass. We discussed before. Okay, given mass divided by molar mass. Substitute value of n over here. So you will get m divided by small letter m divided by mv equal to p by RT. Okay, we know mass per unit volume. M by V mean mass per unit volume, that is density. So D by M equal to P by RT. Okay, D by M equal to P by RT. What is M here? M mean it is molar mass. So molar mass of a given gas is, bring M over here. Okay, so D already here. So dRT divided by P. This is the equation to find molar mass. Okay, so you have a gas, its density, pressure and temperature, universal gas constant. Okay, then you can find its molar mass. Okay, we can find molar mass of a gas with help of these values: density, R we know 8.314, temperature and pressure. Clear? So here we discussed combined gas equation. Also we discussed relation between density and molar mass. Density and molar mass. Okay, how we did this? PV equal to m naught T. Then we did n by V. We did n by V. Okay, we found the equation for n by V. Then we substitute the value of n over here. Mass by m divided by mv. Mass per unit volume mean density. We substitute the value d. Okay, after we found molar mass is equal to dRT divided by P. So you remember this final equation, molar mass is equal to dRT divided by P. Okay. Okay, next one here, last point in this video, we have to discuss here partial pressure. Dalton's law of partial pressure. Dalton's law, it is related to partial pressure. Okay, according to Dalton's law, total pressure of a mixture of gas, what type of these gases? These gases are non-reacting gas. Total pressure exerted by a mixture of non-reacting gases will be equal to sum of partial pressure of individual gas. Okay, see here you have three different gases, okay, and these three different gases are non-reacting gases. For example, helium, neon, argon. These are three different non-reacting gases you mixed in a container. Three different non-reacting gases you mixed in a container. So the total pressure of whole gases, the total pressure of total gases will be equal to sum of individual pressure, sum of partial pressure of individual gas. What do you mean by partial pressure? You have a container with it, you have a container which contains three different gases. Pressure exerted by one gas out of three gas. Okay, imagine you have a container, okay, and here three different gases, okay. So there is a total pressure by three different gases. Out of total pressure exerted by one gas, that is partial pressure of these gases, okay. So you have a mixture of gases, so there is a total pressure. Out of total pressure of one individual gas, that is called partial pressure, okay. So here Dalton's law saying total pressure of a non-reacting gas, total pressure of a mixture of non-reacting gas will be equal to sum of partial pressure of individual gas, okay. That is this equation, it's saying total pressure will be equal to P1, P2, P3. P1, P2, P3 mean P1 mean partial pressure of first gas, P2 mean partial pressure of second gas, P3 mean partial pressure of third gas, okay. When you add all this partial pressure, it will be equal to total pressure. That is Dalton's law. So Dalton's law, it is related to partial pressure. I told you what is partial pressure. Clear? After that you consider three different gases, okay, three different gases at the same temperature, three different gas, each gas same temperature, same volume, but they have different pressure because they are different gases. They have different pressure, P1, P2, P3, okay. According to ideal gas equation, we know PV equal to nRT. I told you pressure is different, so P equal to nRT divided by V, okay. This is our normal ideal gas equation, PV equal to nRT, P equal to nRT by V. We know pressure for three different gases are different, so we can say P1 equal to N1 RT divided by V, okay. N1 RT divided by V. Temperature and volume is same for all three gases, so no need to say T1, V1, no need to mention, because temperature and volume for three different gases are same. Only difference, their N value will be different because they have different gases, they have different N value. R also same because it is universal gas constant. So you can say P1 equal to N1 RT divided by V. P2 equal to N2 RT divided by V. P3 equal to N3 RT divided by V, okay. P1 N1 RT divided by V, P2 N2 RT divided by V, P3 N3 RT by V, okay. So according to Dalton's law, we can say total pressure PT equal to P1 plus P2 plus P3. What is P1? P1 means N1 RT by V, N2 RT by V, N3 RT by V. Here we know N1, N2, N3. It is N1, N2, N3. It is different. RT by V, it is common. So we can take RT by V outside. Then you can write N1 plus N2 plus N3 into RT by V. Okay. I think you understand till this one. Okay, so here I said we have three different gases, P1, P2, P3. Their temperature and volume is same. We know ideal gas equation PV equal to nRT. So P1 equal to nRT divided by V. For P1, N1 RT by V. P2, N2 RT by V. P3, N3 RT by V. Then total pressure will be, we will get like this, N1 plus N2 plus N3 RT divided by V. Next step we have to do here, we know total pressure. Next one we have to do P1 divided by PT. Do this one, P1 divided by PT. So look here, P1 divided by PT. What is PT? PT means N1, N2, N3 divided by RT by V. Okay, so PT, look here, N1, N2, N3, and also here it's coming like this, here divided by V, okay, divided by V, N1, N2, this is PT over here, N1, N2, N3, divided also here RT by V. What is P1? P1 means N1 RT by V. N1 RT by V. So you can see here this term is same, RT by V, RT by V. So you can cancel this. So this term will be neglect. It will be cancelled. So what will be left? P1 by Pt equal to N1 divided by N1 plus N2 plus N3. What is N1? Number of moles of first component divided by total number of moles of component. N1, N2. We know there are three gases. Okay, so N1 means number of moles of first component, N2 means number of moles of second component, N3 means number of moles of third component. So here it is total number of moles of component. Number of moles of first component divided by total number of moles of component. What is it? It is mole fraction. It is mole fraction. Mole fraction is represented by the letter chi. Okay, so here N1 divided by N1 plus N2 plus N3, it is mole fraction of first component. So we can write here P1 by Pt equal to mole fraction chi 1. So P1 equal to, bring Pt over here. So P1 equal to Pt into chi 1. P1 equal to Pt into chi 1. Clear? So this is the equation, P1 equal to Pt into chi 1. Similarly, you can do here, this is your Pt, okay, you can do at homework, do P2 divided by Pt. Do same like this, P2 divided by Pt. So finally, you have to get P2 equal to Pt into chi 2. You will get here N2 divided by N1 plus N2 plus N3. That is mole fraction of second component chi 2. See, after that you can do P3 divided by Pt. So you will get here N3 divided by N1 plus N2 plus N3. That is mole fraction of third component, that is chi 3. So you will get here P1 equal to Pt into chi 1. P2 equal to Pt into chi 2. P3 equal to Pt into chi 3. Okay, so imagine there are many components. So ith component Pi equal to Pt into chi I. You can write this common equation, Pi equal to Pt into chi I. So remember this, okay, P1 equal to Pt into chi 1. So you can find different value using this type of equation. Okay, so this is the relation between partial pressure and mole fraction. Relation between partial pressure and mole fraction. Okay, so these are the things we have to discuss in this video. You can review video once again. So thank you for watching this channel. Okay.